next topic for today is enzyme kinetics. Enzyme kinetics is the study of the rate of the enzyme catalytic reaction. The rate of the reaction is determined by how quickly the substrates are consumed or how quickly the products are formed. When we have a look at this equation, the rate of the forward reaction from substrate to the product is determined by the change of the substrate concentration divided by the time. And the sign for this term should be the negative sign because the substrate are consumed. Whereas from the reverse reaction from product to substrate is determined by the change of product concentration divided by the time. And the sign for this term should be the positive sign because the products are produced. The next term that you should know for the enzyme kinetic is the rate constant. The rate of enzyme catalysis reaction is depending on the rate constant or K. And the rate of enzyme is usually depend on the concentration of substrate or the concentration of products. When we have a look at this equation, the rate constant for the forward reaction from substrate to product is K1. And when we calculate the rate of the forward reaction, the rate of forward is equal to K1 multiplied by concentration of substrate. And when we have a look at the reverse reaction from product to the substrate, the rate constant is K minus 1. And the rate of the reverse reaction is K minus 1 multiplied by the concentration of the product. And remember that when this reaction achieves the equilibrium, the rate of the forward equal to the rate of the reverse reaction. But notice that K1 not necessarily equal to K minus 1. They will be the same only if the concentration of substrate equal to concentration of the product at equilibrium. The rate constant is independent of substrate and product concentration as described by Arrhenius equation here. From the Arrhenius equation, the rate constant or K is equal to AE to the power of minus EA divided by RT. As you can see from this Arrhenius equation, there are no substrate or product concentration involved, so we can say that the rate constant is independent from the substrate and product concentration. Then we can calculate the rate constant by this equation, where K is the rate constant, A is the constant of each chemical reaction according to collision theory. A is the frequency of collision in the correct orientation. That means if the substrate and enzyme have a high frequency to meet each other, so A is increased, then the rate of reaction also increase if A increase. The next one is E. E is the mathematical constant that equal to 2.7 something. Then EA. EA is the activation energy. If you remember from the reaction coordinate diagram. The activation energy or the delta G++ is the difference between energy level of ground state and transition state. If AE is decreased, so the rate constant is increased. As you can see from the equation, the EA have a negative sign. So then if EA is decreased, so the rate of the reaction will be increased. Whereas R is the universal gas constant and T is the absolute temperature in Kelvin. So from here we can calculate the rate constant from Arrhenius equation. In conclusion, the enzyme increase the rate of the reaction by lowering the activation energy or EA, which will increase the rate constant or K. In order to study the behavior of enzyme, we have to study the enzyme kinetic. And one way to study the kinetic is by plotting this curve. On the curve, the y-axis is a reaction rate or initial velocity, and the x-axis is the substrate concentration. The way to plot this curve is doing the experiment in the test tube. Let's imagine in the experiment at first step, we have only enzyme in the test tube, so the concentration of substrate is 0 at this point. That means no substrate bind to enzyme. So the reaction rate or the velocity of the reaction is 0 also at the first point. Then we add a certain amount of substrate to the test tube and measure the rate of the reaction. So we got this point on the curve. And then continue add the substrate and measure the rate like this. So from this, we got this hyperbola curve. What the curve tells us is at the beginning, when we have a little amount of substrate here, the curve resembles as the state line here like this. That means in the initial step, when we add a small amount of substrate, the rate of enzyme reaction is directly in proportion to the concentration of substrate. But when we increasing the concentration of substrate at some point, the slope begin to decrease and the curve begin level off and approach the maximum of velocity. So from here we got the hyperbola curve like this. In conclusion, in the first step, the rate of the reaction is in the proportion with the concentration of substrate. Then after this some point here, the curve is out from the state line. If we increase the concentration of substrate, the rate of the reaction is not in the proportion with the concentration of substrate. In order to calculate the rate of the reaction, first we will have a look in this simple enzymatic reaction. At the first step, enzyme combine reversible with form ES complex here. The formation of ES complex is occur in the fast rate in the area. Then in the second step, the ES complex break down into enzyme and product in the slower rate. Here, the breakdown of ES is occur in the slower rate when compared with the formation of ES. Then from this, in the early of the reaction, the concentration of product is too small because in the beginning of the reaction we got only small amount of the product. Then we can assume that the reverse reaction or K minus 2 here can be ignored. Then to calculate the rate of the reaction, we have to have the equation that can measure easily in the experiment. In this curve here, the initial velocity or the reaction rate is determined by the breakdown of the ES to form the product. So the velocity is equal to the rate constant K2 multiplied by concentration of ES complex. But in real life, the ES complex in this equation is not easily measured because it's a transient complex. So if we cannot measure the concentration of ES product, we have to find the alternative way for the experimental measurement. First, we introduce the term ET. ET is the total enzyme concentration, and ET subtract by ES mean the free or unbound enzyme, because ET is total enzyme and ES is the bound enzyme. So ET subtract by ES is the free or unbound enzyme. Then the concentration of substrate or S here is far greater than the ET. As I told you in the earlier, we need only the little amount of enzyme in the reaction. So when we compare the concentration of substrate and enzyme, concentration of substrate is far greater than enzyme. Then in the first step, the rate of formation and breakdown of ES are determined by the rate constant. For the rate of formation, we can determine by the rate constant K1. Whereas for the breakdown of ES, we can determine by K minus 1 and K2 here. The rate of the formation is equal to the rate constant K1 multiplied by the concentration of the free enzyme here and the concentration of substrate. This is the rate of ES formation, whereas the rate for the ES breakdown is equal to K minus 1 multiplied by concentration of ES plus K2 multiplied by concentration of ES. In the second step, we now make an important assumption. At steady state, the concentration of ES is constant, so the rate of the formation is equal to the rate of the breakdown here. Then we solve the equation by multiply out at the left side. Multiply this S out here. Then we got this term. And simplify for the right side here. So we got this term in the right side. And then we adding the term K1 multiplied by ES and S to both sides here and here. So we got this equation. Then we solve this equation for ES at the left side, and then we got this term. Then we combining the rate constant into one space like this. This term K2 plus K minus 1 divided by K1 is defined as the Michaelis constant or Km. Then substituting this into the equation. Then express V0 in the term of ES by substituting the right side by this equation. V0 is equal to K2 multiplied by concentration of ES. If you remember from this curve that we can calculate the rate by this reaction. Then substitute this into the equation. So we got this. Because the maximum velocity or Vmax is occur when the enzyme is saturated. That means we achieve Vmax when all enzymes in the experiment are bound with the substrate. Then the ES should equal to ET at Vmax. That means at maximum velocity, the bound enzyme is equal to the total enzyme. So we can define Vmax as K2 multiplied by concentration of total enzyme. Then from the equation, we can substitute this term as Vmax here. Then here we got the equation that we call the Michaelis-Menten equation. This equation is the rate equation for one substrate enzyme catalytic reaction, and this shows the quantitative relationship between the initial velocity or V0, Vmax, and concentration of substrate, which all terms are related to the Michaelis constant or Km. And notice that this Km has a unit of concentration. Then we will have a look how we can interpret the Michaelis-Menten equation. From this Michaelis-Menten equation, an important numerical relationship emerges from this equation in the special case when V0 is exactly 1/2 of Vmax. So from here you can substitute V0 as 1/2 of Vmax at the left side here. Then on dividing by Vmax, we obtain this equation. After that, we solving for Km. Then we got this Km is equal to concentration of substrate when V0 is exactly 1/2 of Vmax. From this, we can assume that Km indicates the affinity of enzyme. From the equation, enzyme with high Km have to use the high concentration of substrate to reach the velocity at 1/2 of Vmax. That means enzyme with high Km will show low affinity. In the other way around, enzyme with low Km, they use only small amount of substrate to reach the velocity at 1/2 of Vmax. That means enzyme with low Km show the high affinity. So this is one way to use the Michaelis-Menten equation to interpret the affinity of enzyme. When we look back to the kinetic curve in the term of Michaelis-Menten equation at the initial step here, you can see that the concentration of substrate is around here somewhere. At this point, the concentration of substrate is very low when compared with the Km here. So Km is far greater than concentration of substrate. Then for this term Km plus concentration of substrate, we can assume that is equal to Km. Then for the Michaelis-Menten equation in the initial step shown in this box, V naught is equal to Vmax multiplied by concentration of substrate divided by Km. Whereas at high concentration of substrate here, at high concentration of substrate concentration is far greater than Km when compared with Km. Then this term Km plus concentration of substrate should be around concentration of substrate alone. Then we can ignore Km here. Then the Michaelis-Menten equation for the at the high concentration of substrate, the V naught is equal to Vmax. As you know, Michaelis-Menten plot is the hyperbola curve. This Michaelis-Menten equation can be transformed to the double reciprocal plot. In order to get more useful in plotting experimental data, this Michaelis-Menten equation can be transformed by taking the reciprocal of both sides. Then we get the equation like this. After that, we can separating the component to get this equation. And then in the final step, we simplify them. So we got this equation. This is the double reciprocal plot that we call Lineweaver-Burk equation. When we have a look at this Lineweaver-Burk equation, you can see that this Lineweaver-Burk equation has the same form as linear equation. Y equal to mx plus b, where y is the y-axis, x is the x-axis, m is the slope, and b is the y-intercept. And when we compare this Lineweaver-Burk with the linear equation, you can see that 1 over V naught is the y-axis. 1 over concentration of substrate is the x-axis. Km over Vmax is the slope, and 1 over Vmax is the y-intercept. So this Lineweaver-Burk plot is the plot between 1 over V naught at y-axis, 1 over concentration of substrate at x-axis. the y-intercept is 1 over Vmax, and the slope of this curve is Km over Vmax. So this plot has a great advantage of allowing more accurate determination of Vmax, which can only be approximate from the Michaelis-Menten equation, because for the Michaelis-Menten plot, we can get only the hyperbola curve, but from this Lineweaver-Berg plot, we got the linear curve that we can determine more accurate Vmax from this curve. Okay, next we will move to the next topic, enzyme inhibitors. An enzyme inhibitor is the molecules that bind to enzyme and decrease or stop enzyme activity. Enzyme inhibitors are categorized into two major types. The first one is reversible inhibitor. This reversible inhibitor bind permanent to the enzyme by the covalent bond. And the second type is reversible inhibitor, which attach to enzyme by non-covalent bond. Reversible inhibitors bind to enzyme with the covalent bond, and once they bind together, they cannot be reversed. This kind of inhibitors are generally specific for only one class of enzyme, and a reversible inhibitor doesn't destroy the protein structure, but they specifically alter the active site of enzyme. So when they bind to the enzyme, the substrate cannot bind to the enzyme anymore. Whereas reversible inhibitors, this type of inhibitor attach to enzyme by non-covalent interaction such as hydrogen bond, hydrophobic, or ionic bond. This multiple weak bond between inhibitor and the enzyme at the active site combine to produce the strong and specific binding. This reversible inhibitor can be removed easily by dilute them or dilysis them. And there are four kinds of a reversible inhibitor. The first type of reversible inhibitor is competitive inhibitor. Competitive inhibitor bind to the enzyme active site like this. The substrate and inhibitor compete to access the enzyme active site. So from this we can call competitive inhibition. The competitive inhibitor are often similar in the structure when compared with the real substrate, so they can bind to the same active site. This type of inhibition can be overcome by increase the concentration of substrate. If we increase the concentration of substrate to the efficiency amount, then we can overcome the competitive inhibition. The binding of inhibitor affect the binding of the enzyme. So we can call that the binding of competitive inhibitor will decrease the affinity of the enzyme. And if you remember from the Michaelis-Menten interpretation, when the affinity of enzyme is decreased, so the Km is increased. Whereas Vmax for this competitive inhibitor remain constant because the binding of competitive inhibitor not affect the total number of functional enzymes. And when we have a look at this Lineweaver-Berg plot, as I mentioned, Km is increased, whereas Vmax is still the same. So the slope or the Km over Vmax should be increased. Then the slope of competitive inhibitor will be increased like this. Whereas for the y-intercept, which is 1 over Vmax, because Vmax is still constant, so the y-intercept is still the same. The second type for reversible inhibitor is uncompetitive inhibitor. Uncompetitive inhibitor bind only to enzyme substrate complex like this. This type of inhibition decrease the total number of functional enzymes, result in Vmax is decreased. Whereas for Km also decrease because when the inhibitor bind to the ES complex, the inhibitor increase the affinity of the enzyme substrate complex. So when we have looked at the Lineweaver-Burk plot for the uncompetitive inhibition, you can see that Vmax is decreased. So 1 over Vmax is increased. Then the y-intercept is increased. Whereas for the slope, Km is decreased and Vmax also decreased. So the slope still the same, as you can see here. The third type is mixed inhibitor. Mixed inhibitor bind at separate site, not at the active site, but may bind to either enzyme alone like this, or bind to the ES complex like this. Mixed inhibitor increase the Km because the binding of mixed inhibitor affect the binding of the substrate. Or we can say that mixed inhibitor decrease the affinity of enzyme. Whereas for Vmax, Vmax is decreased because mixed inhibitor decrease the total number of functional enzymes. This type of inhibition can be reduced, but we cannot overcome by increasing the concentration of substrate. And when we have a look at the Lineweaver-Burk plot, when Vmax is decreased, so 1 over Vmax is increased. Then as you can see, the y-intercept is increased. Whereas for the slope, when Km is increased but Vmax is decreased, so the slope is increased. And the fourth type of reversible inhibitor is non-competitive inhibitor, which is one form of mixed inhibitor. Non-competitive inhibitor bind to the enzyme in the same way as the mixed inhibitor. They bind at the separate site, not in the active site, but may bind either with the enzyme alone or bind with the enzyme substrate complex. The difference between non-competitive inhibitor and mixed inhibitor is the binding of non-competitive inhibitor reduce the activity but does not affect the binding of the substrate. So the Vmax is decreased because the inhibition decreases the total number of functional enzymes. But Km will remain the same because the binding of non-competitive inhibitor not affect the binding of the substrate. And for the Lineweaver-Burk plot, when Vmax is decreased, so 1 over Vmax is increased, the y-intercept is increased. But for the slope, the Km is still the same and Vmax is decreased, so the slope is increased. So in the non-competitive inhibitor, when we increase the concentration of inhibitor, the slope will increase like this. This table is a conclusion of these four types of reversible inhibitor that I told you already, so you can have a look this conclusion by yourself. Okay, next we will have a look at the regulatory enzyme. What is regulatory enzyme? In the cellular metabolism, there are many enzymes work together. So the first enzyme of the sequence, we call it regulatory enzyme. Regulatory enzyme is an enzyme in the biochemical pathway which regulate the pathway activity. The activity of regulatory enzyme are modulated in variety of ways. First, regulated by allosteric enzyme by using the non-covalent binding. And second, regulated by reversible covalent modification. Okay, let's have a look at the allosteric enzyme regulation first. Allosteric enzyme contain two binding sites. One used for binding with the substrate that we call the active site. And another type of binding site is bind to allosteric effector that we call regulatory site. Allosteric enzyme composed of several subunits. And there are two types of allosteric effector that can bind to the allosteric enzyme. The first type of allosteric effector is positive effector, or we can call activator. The second type of allosteric effector is negative effector, or we can call inhibitor or repressor. There are two forms of allosteric enzyme that can be found in the normal condition. We can find both active form of allosteric enzyme and inactive form of allosteric enzyme. This figure shows the allosteric enzyme regulation. Let's start with the repression regulation first. This is allosteric enzyme, which contain the active site that will bind to the substrate and the regulatory site that will bind to allosteric effector. In the absence of allosteric effector, this allosteric enzyme is in the active form. In the repression regulation, the repressor here will bind to the regulatory site here. And then they change the conformation of the active site of this enzyme. So the substrate cannot bind to the enzyme and they change into the inactive form here. This is the meaning of repression regulation. Whereas for the activation regulation, in the absence of allosteric effector, the allosteric enzyme is in the inactive form. But in the presence of this activator, the binding of activator to the regulatory site lead to the activation of enzyme. They change the conformation of the binding site, the active site. So the enzyme turn to be active form. They can bind to their substrate. This is the meaning of activation regulation. The second way that regulatory enzyme used to regulate the pathway activity is covalent modulated regulatory enzymes. The active form of enzyme and inactive form of enzyme are altered by using the covalent modification, which catalyzed by altered enzyme. as you can see from this figure, we have enzyme A that catalyze the formation of covalent bond between the chemical group and enzyme. This enzyme A can form the covalent bond between them. And we have the second enzyme, enzyme B. Enzyme B catalyze the breakdown of covalent bond. This enzyme can break down the covalent bond and then we get the chemical group and free enzyme like this. From this, you can see that they can regulate the enzyme by alter the binding site and can change enzyme to active or inactive form depend on enzyme that used to regulate them. So now we move to the last topic of our lecture today, classification and nomenclature of enzyme. Okay. Enzymes are classified by the reaction they catalyze and have been identified by two classification systems. The first system is the recommended name or the trivial name. For trivial name, the enzyme can be named by the substrate, reaction type, or functional profile, then add ASE or S as a suffix behind them. For example, urease that used for catalyze the hydrolysis of urea. But some enzymes are used the name as its historical name. For example, pepsin or trypsin. The second system is systematic name. For systematic name, we use the enzyme commission number or EC number, which is the classification of enzymes based on the chemical reactions they catalyze. In systematic name, there are four numbers that indicate the major class, subclass, sub-subclass, and enzyme serial number. For example, the dipeptide aminopeptidase, which have the code like this. And when we have a look at the major class for this enzyme, number 3 is mean this enzyme is hydrolase enzyme. The subclass for this one is number 4. That means this enzyme is hydrolase that act on the peptide bond. For the subclass, number 11, that means this enzyme is hydrolase that cleave off the amino terminal amino acid from the polypeptide. And then the last number, serial number, is number 4, which means they are those that cleave off the amino terminal end from the tripeptide. So this is the way that we name the enzyme by systematic name. Okay, so this is all of my lecture today. The reference for this lecture came from Nature Principles of Biochemistry, 4th edition in Chapter 6, Enzymes. Okay, so thank you so much for your attention.